DNA strands run anti-parallel to each other. Notice that one strand begins with 3' and ends with 5', and then the other strand begins with 5' and ends with 3'. And DNA strands split at the origin of replication. So if this were to replicate, and then the origin of replication would be about in the center. There are multiple origins of replication in a full DNA molecule for eukaryotes. The origin of replication is identified by specific sequences of the base pair in the DNA molecule. And then the helicase is an enzyme that helps break down the hydrogen bonds between the two DNA strands. So then your DNA will go, the helicase will go through your DNA, breaking the hydrogen bonds between the adenine, thymine, guanine, and cytosine. Then to break this. And then this DNA, once the DNA splits, this will cause two replication forks to form between them. So there will be two, one right here and then one on the other side, forming a DNA molecule bubble.
Topoisomerase helps to relieve the structural pressure that is put on the DNA molecule after the fork. Single-strand binding proteins bind to the separated strands to keep them from coming back together.
Primase is an enzyme that catalyzes the production of an RNA primer. An RNA primer is a small strand of RNA that allows DNA polymerase III to begin the process of DNA replication. This is because DNA polymerase III can only add onto an existing strand which the RNA primer provides. And DNA polymerase III is an enzyme that catalyzes the addition of new nucleotides to the III end of the new DNA strand, using the complementary DNA strand as a template.
This structural constraint of DNA polymerase III, where it can only move from the 5' to the 3' end, means that there will be two leading strands and two lagging strands for each complete DNA replication bubble. In this case, where we have half a bubble, there will be one leading strand and one lagging strand. The leading strand is continuously added onto by DNA polymerase III, requiring only one primer to initiate the process. It moves towards the replication fork, and it looks something like this, where nucleotides are added continuously. The lagging strand, however, is a series of nucleotide sequences that each require an RNA primer to work, and they move away from the replication fork. And so here you see 3 primers, and the DNA nucleotides would be arranged from right to left away from the replication fork. These fragments are called Okazaki fragments, and their purpose is to overcome the structural constraint of DNA polymerase III.
Good luck.
DNA polymerase I removes RNA from the strand and replaces it with DNA. It also proofreads and fixes any errors in the strand.
Once DNA polymerase I removes all of the RNA primers from the lagging strand, the discontinuous Okazaki fragments are joined by an enzyme called DNA ligase, as so.
That's it. The final product of DNA replication is 2 double-stranded DNA helicals that are, in theory, identical to each other. Each DNA helix has one strand from the original and one strand that was created. It is for this reason that the replication of DNA is semi-conservative.